So in this video I'm going to discuss the question in thermal and statistical physics which appeared in JEST 2018 examination. So let's continue with the first problem. The statement is, when a collection of two level system is in equilibrium at temperature T naught, the ratio of the population in the lower and upper level is 2:1. When the temperature is changed to T, the ratio is 8:1. Then we have to find the appropriate relationship between T and T naught. Okay, so let's try to understand this problem. So we are having a two level system. It's basically a collection of two level system. Okay, and we are assuming that let n1 be the number of particles in the ground state and n2 be the system in the excited state. Okay, so the relationship between the particle in the excited state with those in the with the total number of particles, or the system you can say, that is given by n, that is equal to n0 exponential minus e upon kVt. That's the general result. Okay, so let's call this as equation 1. Now we are given that the ratio of the population in the lower and upper level, that is 2:1, and this is at temperature T naught. Okay, so that means we are given a condition where n1 divided by n2, that is equal to, so when here we will substitute n1 because n naught it's a total number. Okay, so this is this will be equal to exponential, so n naught and n naught, that will cancel with each other. Okay, so and then this is E2 minus E1 upon kb T naught. So and this is given to be equal to 2/1. Okay, so taking logarithmic on both sides, we obtain E2 minus E1 divided by kb T naught, that is equal to ln2. Okay, so let's call this as equation 2. Now it's given that further the next condition is that when temperature is changed from T naught to T, this ratio, the same ratio, that is n1 divided by n2, that is equal to exponential E2 minus E1 divided by kb T. Now it's T, not T naught. Okay, and that is equal to 8. Okay, so again taking exponential on both sides, again we obtain E2 minus E1 upon kBt, that is equal to ln 8, and that is equal to 3 ln 2. Okay, so let's call this as equation 3. Now divide 2 by 3. So 2 divided by 3, it gives us T upon T naught, that is equal to ln 2 divided by 3 ln 2, or that is equal to 1 by 3. So this means T naught is equal to, so this means T naught is equal to 3 times T. So that means C is the correct option here. So let's continue with the next problem. The statement is, a collection of n interacting magnetic moments, okay, each of magnitude mu is subject to a magnetic field H along the z direction. Okay, each magnetic moment has a doubly degenerate level of zero energy. So we are given that each magnetic moment, it is having a doubly degenerate level of zero energy. So energy is 0 and the corresponding degeneracy is 2, and two non-degenerate levels of energy minus mu h and plus mu h, and two non-degenerate level of energy minus mu h with g is equal to 1, and another level of energy mu h of energy mu h and degeneracy 1. Okay, the collection is in thermal equilibrium at temperature T. The total energy ETH of the collection is how much? Okay, so we can, this is a very simple problem and we can solve this by making use of the partition function approach. Okay, so here first of all we are going to find the partition function for one single spin. Okay, so for one single spin the partition function is Z1, that is equal to we will apply the basic definition of the partition function, that gi exponential minus beta ei. Okay, so here this is equal to g1 exponential minus beta e1 plus g2 exponential minus beta e2 plus g3 exponential minus beta e3. So here e1, this is e1, okay, and this is e2 and this is e3, okay, and g1 is equal to 1, g2 is equal to 2 and g3 is equal to 1. Okay, so we will substitute the corresponding values, so that z1 is equal to 1 into exponential minus beta into minus mu h, so that is equal to mu h upon kt, beta mu h basically, that is mu h upon kbt, and then g2 is equal to 2 exponential minus beta into e2, which is 0, that is exponential 0, which will be 1 ultimately, plus g3, that's 1 into exponential minus beta into mu h, so that is minus mu h upon kbt. Okay, so this is equal to, I'm writing this 2 in the beginning, 2 plus exponential mu h upon kt plus exponential minus mu h upon kt, and this is equal to 2 plus 2 cos hyperbolic mu h upon kt, that's the single spin partition function. Okay, and from here I can write the partition function for the n spins. Okay, so Zn is equal to Z1 power n. So I can write this because we can treat the spins to be distinguishable, in a sense that they are fixed at the, or they are localized. Okay, so because spins are localized. Okay, so that means the n spins partition function is equal to 2 plus 2 cos hyperbolic mu h by kt power n, that is the n spins partition function. So let's call this result as equation 1, and from here we can determine the total average energy U, that is equal to minus curly beta of ln Zn, and that is equal to minus n curly beta of ln 2 plus 2 cos hyperbolic mu h upon kt. Okay, and this is equal to minus n upon 2 plus 2 cos hyperbolic mu h by kt. Okay, and then again the differential of this term with respect to beta, which is 1 by kt, and so that will give us 2 sine hyperbolic mu h by kt, and then multiply by mu h, because it's a beta mu h, it's differential with respect to beta, that will give us a mu h only. Okay, so this is equal to, so let me insert a page here, so that after solving it we obtain the final answer U, that is equal to minus n mu h sine hyperbolic mu h upon kbt, okay, divided by 1 plus cos hyperbolic mu h by kbt. Okay, so that's our final answer. So this gives us the total internal energy, and let's see, okay, so this matches with the option A, so therefore option A is the correct one here. So let's continue with the next problem. The statement is, in a thermodynamic process, the volume of 1 mole of an ideal gas is varied as V equal AT minus 1, where A is a constant. The adiabatic exponent of the gas is gamma. What is the maximum amount of heat received by the gas if the temperature of the gas increases by delta T in the process? Okay, so we are given a process where the volume changes with temperature according to the equation volume V, that is equal to A upon T. Okay, where A is given to be a constant. Okay, so we have to find what is the delta Q. What is delta Q? Delta Q is equal to how much? When the process is taking place, there is a change in temperature delta T. Okay, now because V, that is equal to A by T, so this implies dV, that is equal to minus A upon T square dt. Okay, so we will apply the basic definition of the work done, that is work done during a process W, that is equal to P dV. Okay, so P is basically because it's an ideal gas, so and heat received by the gas, if okay, it's 1 mole. Okay, so that means we can replace P, that is equal to RT upon B. PV is equal to RT basically for 1 mole of a gas. Okay, so I'm going to replace P with RT by B, so this is equal to RT dV upon B. That's the work done. Okay, now RT as it is, and then I'm going to substitute the value of V and dV from equation 1. Okay, so RT into 1 by V, so that means this is T by A, T by A, and then dV, so dV is equal to minus A upon T square and then dt. Okay, so this upon solving, so this will give us R dt with negative sign. Okay, so that means this is equal to minus R delta T, because delta T, that's the change in temperature during the process. Okay, so we have obtained the expression for the work done during the process, which is minus R delta T. So let's call this as equation 2. Okay, now if the temperature is changing by an amount delta T, so then the corresponding change in internal energy delta U, that is equal to N CV delta T, or N is given to be unity, so that means that is equal to CV times delta T. Now because if you just take a look at the answers which are given, these are not in terms of CV but rather in terms of gamma. So we have to connect CV with the gamma, and that can be done by making use of the equation which connects CP with CV. So that is CP minus CV, that is equal to R for 1 mole of a gas, and then you divide both sides with CB. CP by CB minus 1, that is equal to R by CB. So Cp by Cb, that is gamma, so gamma minus 1, that is equal to R by Cb, or Cv is equal to R upon gamma minus 1. So make this substitution here, so that gives you delta U, that is equal to R delta T upon gamma minus 1. Let's call this as equation 4. Okay, so now from the first law of thermodynamics, we have delta U, that is equal to delta Q minus W, that's the first law, and from here delta Q, that is equal to delta U plus W. Okay, so delta U is how much? That is R delta T upon gamma minus 1, and W is minus R delta T. Okay, and after solving this result, delta Q comes out to be equal to delta Q, that is equal to R delta T into 1 upon gamma minus 1 minus 1, and that is equal to R delta T 1 minus gamma plus 1 upon gamma minus 1. Okay, so this is equal to 2 minus gamma upon gamma minus 1 multiplied by R delta T. So that's the heat exchange involved during the process. And let's see the options that are given to us. So this is option D, which is the correct one, that R delta T into 2 minus gamma upon gamma minus 1. That's the correct option. So let's continue with the next problem. The statement is, for a classical system of non-interacting particles in the presence of a spherically symmetrical potential VR is equal to gamma R cube, what is the mean energy per particle? Okay, gamma is a constant. Okay, so here the mean energy per particle, so basically the mean energy per particle, it's basically the mean kinetic energy plus mean potential energy. Okay, so let's see how we can find it out. So it's literally easy to predict the mean kinetic energy per particle, because a classical system consists of free particle, and a freely moving particle has 3 translation degrees of freedom. So the mean kinetic energy, that is nothing but that is 3 by 2 kBT. Okay, but now the next point is how to determine the mean potential energy. Okay, so the mean potential energy, so here we will apply the given potential, which is given as the potential VR. It's a spherically symmetrical potential VR, that is equal to gamma R cube. Okay, so that's it's a three-dimensional potential basically. Okay, so spherically symmetrical potential, so average value of the potential energy V, so that is equal to 0 to infinity, then the value of the potential, that's VR. Okay, and then exponential minus beta BR. Okay, so that will be equal to exponential minus gamma R cube upon kBT. Okay, and then dB, so I'm writing dB as 4 pi r square dr. Okay, so, and then this is divided by 0 to infinity and exponential minus gamma r cube upon kBT, and then 4 pi r square dr. Okay, yes, so this 4 pi will cancel with 4 pi, and we can substitute the value of VR, which is equal to gamma R cube here. Okay, so this will give us, so 4 pi will cancel with 4 pi, and after substituting the value of VR, so VR is equal to gamma R cube, so we obtained finally, so V, the average potential energy, that is equal to gamma times 0 to infinity r power 5, and then exponential minus gamma r cube upon kt. I'm writing k for the Boltzmann constant. Okay, and then dr, and this is divided by 0 to infinity r square exponential minus gamma r cube upon kt dr, and I'm writing this to be equal to gamma times I1 upon I2. So let's call this as equation 4. Okay, let's call this as equation 4. So now where I1 denotes the integral in the numerator, so that means I1 it is this integral, and I2 corresponds to this integral. So we will determine these two integrals separately. So let's first continue with the integral I1. Okay, so I1 is equal to I1 equals 0 to infinity r power 5 exponential minus gamma r cube upon kt dr. Okay, so here we are going to make a substitution, both the same substitution in the numerator as well as in the denominator. So here I'm going to replace r cube is equal to u, so that r equals u power 1 by 3, and further as r goes to 0, u also goes to 0, and as r goes to infinity, u also goes to infinity. Okay, and because we require r power 5 in the I1 and we require r square in the I2. Okay, so from this result we can write r power 5 equal to u power 5 by 3 and r square equal to u power 2 by 3, and further we also need dr. Okay, so dr can be written as, from r is equal to u power 1 by 3, so dr will be 1 by 3 u power 1 by 3 minus 1 du, and this is equal to 1 by 3 u power minus 2 by 3 du. Okay, so with these results the I1 comes out to be equal to I1 will be, it is 0 to infinity r power 5, that is u power 5 by 3, and then exponential minus gamma u upon kt, and then the value of dr, which is equal to 1 by 3 u power minus 2 by 3 du. Okay, and this after solving it 0 to infinity, so u power 5 by 3 minus 2 by 3, so that will give us u. So u exponential minus gamma by kt, exponential minus gamma upon kt u du. Okay, so this can be solved by integration by parts, so that we will do in on the next page. So let's move to the next page. Okay, so I1 is further equal to I1, that is equal to the I'm taking constant outside, 1 by 3 outside. Okay, let me check whether I've taken the factor of 1 by 3 along with or not. Yes, it should be 1 by 3 here. Okay, so 1 by 3 outside, and then integration by parts, first into integral of second, so that is exponential minus gamma by kt u, and then divided by minus gamma by kt, and when the limits changes from 0 to infinity, and minus integral of derivative of first, which is 1. Okay, and then integral of second, so exponential minus gamma by kt u divided by minus gamma by kt du. Okay, so this term, it goes to 0 in the, when limit goes to infinity, the exponential term will goes to 0, and when the limit goes to 0, then this u, it will goes to 0. So ultimately this will contribute to 0. Okay, so I1, it will be equal to 1 by 3. So again, so this minus and this minus, this will become plus, so 1 by 3 into kt by gamma, kt upon gamma, and then it's a integral of exponential minus gamma by kt u du. Okay, so this will be equal to exponential minus gamma upon kt, okay, divided by minus gamma upon kt 0 to infinity. Okay, and this, when limit goes to infinity, so this will become 0, but when it goes to 0, this will give a unity, but with the negative sign, so negative and negative, that will become plus. So ultimately this is equal to 1 by 3 kt upon gamma, its whole square. So that's the value of I1. Okay, so let me check the number I have given already. So I have given up to equation 4, so let me call this as equation 5. Okay, so we have evaluated I1. Similarly, we can evaluate I2. So I2 will be equal to I2, that is equal to 0 to infinity r square exponential minus gamma by kt r cube and then dr. So we have already done this substitution. So same substitution we are going to use. So with replacing r square with u power 2 by 3. Okay, so this we have already done here. So all these things we have already done. So we are making the same result here. So as r goes to 0, u goes to 0, and r goes to infinity, u also goes to infinity. Okay, so this is further equal to 0 to infinity u power 2 by 3 exponential minus gamma upon kt u and then dr, which is equal to 1 by 3 u power minus 2 by 3 du. Okay, and this can be further solved with the integration by parts. So this is equal to u power 0, basically u power 2 by 3 minus 2 by 3, so u power 0, that is unity. Okay, so that's from 0 to infinity, and then u power 0, that's 1 into exponential minus gamma by kt u and then du. Okay, so this can be solved quickly by so this is basically equal to, so a factor of 1 by 3 outside, 1 by 3 and then exponential minus gamma by kt u upon minus gamma by kt and limits of integration from 0 to infinity. So this is equal to kt by gamma 3 gamma. Okay, that's equation 6. Okay, so equation 4, 5 and 6. So that means equation 4, 5 and 6 implies the average value of V, that is equal to gamma times I1 upon I2. So that is gamma times into 1 by 3 kt by gamma its square divided by I2, which is equal to kt by 3 gamma, kt upon 3 gamma. Okay, so this is nothing but this is equal to kt. So therefore the total the average energy per particle, that is equal to the kinetic energy T plus average value of the potential energy. So that is equal to, so remember that this is we are doing this calculation for the single particle. So 3 by 2 kt, that's average translation kinetic energy plus potential energy kbt, and this is equal to 5 by 2 kbt. Okay, so therefore option B is the correct one here. So let's continue with the next problem. The statement is, an ideal fluid is subjected to a thermodynamic process which is described by rho, that is equal to Cv minus alpha, and P, which is equal to n rho power gamma, where rho is the energy density and P is the pressure. For what value of n and gamma the process is adiabatic if the volume is changed slowly. Okay, so it's given that rho, that's the energy density, rho that is the energy density, that's energy per unit volume. This implies I can write U, that is equal to rho into V, but rho is given as Cv power minus alpha here. Okay, so that means I can replace rho with Cv power minus alpha and then multiply by another V here, so that this is equal to, so that U, that is equal to Cv power 1 minus alpha. So let's call this as equation 1. Okay, now the pressure is given as P equals N rho power gamma. Okay, so rho is equal to, so okay, so we are going to substitute the value of rho, that is CB power minus alpha. Okay, so that means that is N, and then rho is equal to CB power minus alpha and its power gamma. Okay, so that pressure, from here we conclude that P is equal to N C power gamma, and then inside the bracket we are having B power minus alpha and its power gamma. So let's call this as equation 2. Okay, now the question is, for what value of N and gamma the process is adiabatic. Okay, process is adiabatic, that is dq that is equal to 0. Okay, so we are having the relationship, the modified form of the first law of thermodynamics, that is dq that is equal to du plus pdv, or I can write tds equal to du plus pdv. Okay, it's a modified form of the first law of thermodynamics. Okay, so because we are talking about a process to be adiabatic, so that is tds that is equal to 0, because this is nothing but this is dq. Okay, so therefore the necessary condition that we have to ensure that it is valid, that is du plus pdv, this is equal to 0. So let me call this as equation 3. Okay, now ultimately we have to prove that du plus pdv that is equal to 0, and that will allow us to obtain the necessary condition that can be imposed on n, gamma and alpha also. Okay, so from equation 1 I can obtain the expression for du, because ultimately I require du and pdv. This, if I am having the value of these two quantities, then I can obtain the necessary condition. Okay, so from equation 1 du that is equal to, so du that is c, okay, it's a constant, and then 1 minus alpha b power 1 minus alpha minus, that is nx power n minus 1. Okay, and then dv. Okay, so that means this is equal to, c into 1 minus alpha and v power minus alpha, 1 and minus 1 will cancel, b power minus alpha dv. Okay, so let's call this as equation 4. So this is the value of du. Okay, now similarly from equation 2, we can write the p dv. So p, we will make use of the equation 2, and then we will multiply it with dv. Okay, so p dv that is equal to n c power gamma and then b power minus alpha and its power gamma and multiply by dv. So let's call this as equation 5. Now with the help of equation 3, 4 and 5, so that is basically we are going to substitute 4 and 5 in equation 3. Okay, so that we obtain, so equations 3, 4 and 5. Okay, 3, 4 and 5 implies that, so I'm going to substitute the value of du, which is c into 1 minus alpha and then v power minus alpha dv, that's du plus pdv. So that's equation 5. Now I'm substituting the value of pdv from equation 5, that is n c power gamma and b power minus alpha power gamma, that is alpha gamma and then dV that is equal to 0. That is du plus pdv that is equal to 0. Okay, so that means I can take cb power minus alpha outside, and then inside the bracket I'm left with 1 minus alpha, okay, plus n c power gamma b power minus alpha gamma, and because we have taken cb power minus alpha outside, so I'm dividing here with cb power minus alpha, and then this entire expression multiplied by dv, and that is equal to 0. Okay, and this upon solving, so we are left with cb power minus alpha 1 minus alpha, and then upon solving the second term 1 minus alpha plus n, and then c power gamma minus 1, c power gamma minus 1, okay, and then b power minus alpha gamma, and then plus alpha, and then dv that is equal to 0. Again this can be rewritten as cb minus alpha 1 minus alpha, and then n c power gamma minus 1, and b power, you take alpha outside, and then 1 minus gamma, and then dv that's equal to 0. So from here we notice that this is going to be equal to 0 because this cannot be equal to 0. Okay, so this is equal to 0 only when gamma, if we take gamma is equal to 1, and when we take gamma is equal to 1, then the expression inside the bracket, this allows us to write that 1 minus alpha, so c power gamma minus 1, so when we are taking gamma as 1, so c power 0 that will give us 1. Okay, and then here also b power alpha into 1 minus 1, that is b power 0, that's also 1, so that's 1 minus alpha plus n, that is also equal to 0. Okay, so when gamma is equal to 1, and then 1 minus alpha plus n, that is equal to 0. So that means in this I can write n is equal to alpha minus 1. Okay, so therefore the necessary condition for this process to be adiabatic, that is C. So that is when gamma is equal to 1 and n is equal to alpha minus 1. Okay, so therefore C is the correct option here. So let's take a look at the next problem. The statement is, a theoretical model for the real non-ideal gas gives the following expression for the internal energy U and pressure P. So we are given two expression for the U and P in terms of parameters A and V. Okay, here A and V are constants. Let V0, T0 be the initial volume and initial temperature respectively. If the gas expands adiabatically, so this is a condition which is supposed to be valid for the expansion for the given gas. The volume of the gas is proportional to, okay, so we have to find the appropriate relationship that connects the volume and temperature of the gas. Okay, so let's see, let's continue with the information that's given to us. We are given internal energy as a function of T and V, and that is equal to A B power minus 2 by 3, okay, plus V power 2 by 3 T square. So let's call this as equation 1. And we are also given the pressure as a function of T and V, which is equal to 2/3 of A B power minus 5 by 3 plus 2 by 3 B V power minus 1 by 3 T square. So let's call this as equation 2. Okay, now we are going to make use of the modified form of the first law of thermodynamics, and which says that TdS that is equal to du plus dw, which is pdv, du plus pdv. Okay, by using the second law of thermodynamics, this is equal to dq. Dq is equal to tds basically. Okay, and since the process is adiabatic in nature, so that means dq will be equal to 0. So this implies du plus pdv, that is equal to 0. So this is the equation 3. Okay, and we have, because for the process to be adiabatic, so this equation must be satisfied. Okay, so from the given information we are going to validate the equation 3 for the given non-ideal gas. Okay, but since it's given that u, because u, it's a function of T and V, it's given to us. Okay, so therefore we can write a small change in the internal energy du, that is equal to du by dt by keeping the second variable constant. Okay, dt plus du by dB by keeping the first variable constant, dV. Okay, now we are going to evaluate du by dt, curly u by curly t at constant volume and curly u by curly b at constant temperature from equation 1. Okay, so therefore this is equal to du is equal to, now du by dt at constant volume. Okay, so by keeping the volume constant, so the first term will not contribute in this case, so we will obtain 2b t b power 2 by 3. So this is the differential that we obtain from this this part. Okay, and then multiply by dt, so multiply by dt. Now the second differential, which is du by dv at constant temperature. Okay, so from here we will obtain two terms. Okay, the first term will be the differential of the this term with respect to v, du by dv, so it will give us a factor of minus 2 by 3 from the exponent, and then the a and v power minus 5 by 3. Okay, I'm putting it inside the bracket because we will obtain another term from the second term by differentiating with respect to v. So plus the exponent, that is 2 by 3 b t square, because t is constant here. Okay, v power minus 1 by 3 and then dB. Okay, dV. So let's call this as equation 4. Now we are having expression for du and we are also having expression for p also. Okay, so we will obtain we will fix the value of du from equation 4 into this equation 3, and the value of p from equation 2 we will substitute in equation 3. So in equation 3 we are going to substitute the value of du and p, and then we will equate the this equation to be equal to 0. So therefore du plus pdv, du plus pdv, that is equal to, now the value of du. Okay, that is here 2b b power 2 by 3 and then t dt, the second then the second term minus 2 by 3 a b power minus 5 by 3 dv. So I'm separating the terms, and then the second term, which is 2 by 3 plus 2 by 3 b t square b power minus 1 by 3 dv. So this is du, the value of du we have substituted. Okay, now plus pdv, plus what is the value of p? It's this equation. Okay, p, and then this equation multiply by dv. Okay, so that means 2 by 3 a b power minus 5 by 3 plus 2 by 3 v power minus 1 by 3 t square, and this multiply by dv, and that should be equal to 0. Some of the terms will cancel, so this will cancel with the first term, this one. Okay, so because dv is outside, so this will cancel with this equation. Okay, now after the, because this is equal to 0, so that finally we will obtain 2b v power 2 by 3 t dt, and that is equal to minus 4 by 3 v power minus 1 by 3 t square dv. So we are having these two terms, so that's why 4 by 3. Okay, so after rearranging the terms by collecting the coefficient of dt and dv on one on respective sides, we obtain t by t square dt, and that is equal to minus 2 by 3 b power minus 1 by 3 dv upon v power 2 by 3. So upon solving, we obtain dt by t, that is equal to minus 2 by 3 dv by db. Okay, and upon taking the logarithmic on both upon solving it or doing the integration, so we obtain ln t, that is equal to ln v power minus 2 by 3. So this implies t is proportional to v power minus 2 by 3, or v is proportional to t power minus 3 by 2. Okay, so therefore option C is the correct one here. Let's take a look at the next problem. The statement is, in an experiment, certain quantity of an ideal gas at temperature T0, pressure P0 and volume V0 is heated by a current flowing through a wire of for the duration of t seconds. Okay, so the volume is kept constant and pressure changes to P1. Okay, if the experiment is performed at constant pressure starting with the same initial condition, the volume changes from V0 to V1. The ratio of the specific heat at constant pressure and constant volume is how much? Okay, so we are given a situation where the same gas, a gas which is initial at we are having an ideal gas. Let's try to understand the problem first. We are having ideal gas at constant temperature T0, pressure P0 and volume V0. Okay, now this gas is heated by two different ways. Okay, the first is the heating at the volume is kept constant, the fixed volume heating. Okay, the one method is fixed volume heating. Okay, and the second method is fixed pressure heating. Fixed pressure heating. Okay, so the point is that for the same duration of time, same current is flowing through the wire. Okay, but the conditions are different. So in a fixed volume heating, so that is here we must make use of the CV, and here we must make use of the CP. Okay, and because it's a fixed volume heating, so that means for this case, because it's an ideal gas, for fixed volume heating, pressure will be proportional to temperature. Okay, so in the first case, when volume is kept constant, the pressure changes to P1. Okay, so initially the pressure and temperature are P0 and T0, and now the corresponding change in the pressure is P1. Okay, so that means for the fixed volume heating, P by T is equal to constant. So that we notice from here. So therefore this implies P0 by T0, that is equal to P1 by T1. Okay, so P1, the change in pressure that's given to us P1, and we assume that corresponding change in temperature is T1. So this implies T1 is equal to P1 upon P0 multiplied by T0. Okay, so, and the corresponding heat exchange that is involved, Q, that is equal to CV delta T. CV delta T at constant volume heating, and that is equal to CV into T1 minus T0. So let's call this as equation 1. Okay, now let's take a look at the second process. It is a constant pressure heating. Okay, so in constant pressure heating, when P is constant, okay, in this case volume is proportional to temperature. Okay, why? Because we are having, because a gas which is ideal gas, PV is equal to RT. So when pressure is constant, then in that case volume is proportional to temperature. Okay, so that means for the initial condition, volume is V naught, temperature is T naught. So V naught by T naught, that is equal to constant, so that is equal to V1 upon T1. Okay, so it's given that if the experiment is performed at constant pressure starting with same initial condition, the volume changes from V0 to V1. Okay, so that's why we have taken V1, and let's say the corresponding change in temperature, it is T1 dash, not T1. Okay, so this implies T1 dash, that is equal to V1 upon V0 multiplied by T naught. Okay, so and the corresponding heat exchange involved in this process, that will equal to, let's say, Q dash, and that will be equal to Cp and the corresponding change in temperature but at constant pressure, and that is equal to, this is equal to Cp and dt, which is T dash minus T naught. So let's call this as equation 2. Okay, now as the gas is ideal, as the gas is ideal, so that means PV is equal to RT, it's valid. Okay, so from here we can write P dV plus V dP, that is equal to R dt. Okay, so for fixed volume process, for a fixed volume process, dV equal to 0, so that means corresponding change in temperature, if I call that as dTV, that's a change in temperature when volume is kept constant. So this equation gives us, because dV that's 0 in this case, so dt will be V by R dP, dTV, that is equal to V by R dP. Okay, and that is equal to V0 by R into dP, which is P1 minus P0. Okay, so let's call this as equation 3. Okay, similarly for fixed pressure process, fixed pressure process dP will be 0. So again from the same equation, now this term will be 0, so dTP in this case, dTP, that will be equal to P by R dB. Okay, it's basically P0 by R. Okay, the initial pressure. Okay, and same way we did here, it's B0 by R. Okay, it's V0 by R, basically P0 by R dV. So that means that is equal to P0 by R dV is nothing but V1 minus V0. So let's call this as equation 4. Okay, now because the same current, this is an important point to note here, because same current flow through system for same time. Okay, so therefore same amount of heating will be produced, so that means Q is bound to be equal to Q dash, because it's given that it's the same current that's flowing through the wire for the same time. So therefore it doesn't matter under what condition we are doing, we are performing the process, but it's the same current that's flowing through the same time for the through the wire. Okay, so therefore the heat that is generated during this time, that will be equal to that will be equal. Okay, so therefore CV dTV is equal to Cp dTP. Okay, or Cb and then multiply by the value of dTV. So dTV value, it's from the equation 3. Okay, so we are making use of equation 3 and 4. So that means V0 by R and multiply by P1 minus P0, that is equal to Cp P0 by R into B1 minus V naught. Okay, so from here we note that Cp by Cv that is equal to V. So R will cancel with R, so that is equal to V naught by P naught into P1 minus P naught upon B1 minus V naught. Okay, that's the ratio of the heat capacity Cp and Cv. Okay, so therefore let's see which option is the correct one. It's V naught by P naught into P1 minus P naught upon B1 minus V naught. So therefore option A is the correct one here. Okay, option A is correct. So let's continue with the next problem. The statement is a frictionless heat conducting piston of negligible mass and heat capacity divides a vertical insulated cylinder of height 2h and cross section area A into two halves. Okay, so we are having a cylinder. Okay, let's try to understand the problem first. Okay, we are having a cylinder whose total height that is given by 2h. Okay, that's the total height of the cylinder, and then we are having a piston which is dividing this cylinder into two equal halves. Okay, so that means it's a weightless piston. Okay, and it's dividing this cylinder into two halves, equal halves. So that means the height, this is h, this is also h. Okay, and we can assume that cross sectional area of the piston, we can assume it to be equal to A. That's the cross sectional area. Okay, now further let's see what is given to us. Yes, the cross sectional area A, that's given to us in two halves. Each half contain 1 mole of an ideal gas at temperature T naught. Okay, so here it's given that N is equal to 1 mole and at the initial temperature is T naught and pressure P naught corresponding to STP, standard temperature pressure condition. Okay, the heat capacity ratio gamma is equal to Cp by Cv, that is given. A load of weight W is tied to the piston and suddenly released. Okay, but before we continue with the next part of the statement, so let's first assign the parameter to the cylinder before attaching the load. Okay, so when so suppose this is the equilibrium position of the piston when there is no load attached to the piston. Okay, now when a load is attached, so let's draw the diagram, the corresponding diagram. Okay, so this corresponds to the initial equilibrium state. This is the position of the piston when there was no load attached to it. Okay, now when a load is attached, so in that case, suppose the piston has moved by a certain distance. So this is the new position of the piston when load is attached to the piston. Okay, and the load is, that is W, weight W. Let's say weight W, and which is mg, where m is the mass of this load. Okay, so let's say that the vertical displacement of the piston is y. Okay, so that now here the height below the piston, okay, it is h minus y, and that above the piston, that is h plus y. Okay, now when sorry, a load of weight W is tied to the piston and suddenly released, after the system comes to equilibrium, the piston is at rest and the temperature of the gases in the two compartments are equal. So let's say now the piston has again come to rest after it's disturbed from the equilibrium position, and then when we are attaching the load, it's displaced from the equilibrium position, and now again it has come to rest. So we are assuming that by, that's the equilibrium position. Okay, so the final temperature is T in both compartment. Okay, so that's the information that's given to us. But now since the piston is moving in the downward direction, the corresponding pressure here, it's P1 and here it's P2. Okay, now the situation will be that P1 it's going to be larger than P2 because the gas inside in the lower portion it is compressed, so the corresponding pressure here it's going to be higher as compared to the initial pressure. Okay, so now we are going to solve this problem. First of all, we will apply the energy balance. Okay, so let's see how we are going to do that. Energy balance. So that means when the piston is moving in the downward direction, it's moving by an amount y. So corresponding change in the potential energy, so that is equal to m g into y, that's height. So that's the because piston is moving by an amount y, so that's a corresponding change in the potential energy. Okay, and we are calling this as W, because W that is equal to mg into y, W into y, and that is equal to the corresponding change in the energy of the gases in two compartment. Okay, so because we are having 1 mole in each of the compartment, the corresponding change in temperature is T minus T naught for each gas. Okay, so for the gas in lower compartment, the change in energy is, let's call that as U1, so that is equal to N Cb and then delta T. Okay, so that is equal to 1 into Cb into T minus T naught. So that's the change in internal energy in the lower compartment. Similarly, the corresponding change in internal energy in the upper compartment, that is N into Cb, the final temperature minus initial temperature. So the total change in internal energy is U1 plus U2. So therefore here I am going to write W into Y, that will balance the total energy change to Cb into T minus T naught. Okay, so let's call this as equation 1. That's the energy balance. And further, after attaching the load, again when the system has again reached the equilibrium, so in that case the net pressure exerted by the weight, that is W by A, okay, that will be balanced by the pressure difference in the lower chamber and upper chamber, which is P1 minus P2. Okay, and that is nothing but, so here we are going to apply the ideal gas equation here, because P that is equal to RT upon B. Okay, so that means P1 will be RT upon volume, which is A, the cross section area of the this piston, multiplied by the height, that is h minus by, into h minus by, that's P1 minus P2 minus RT upon volume, or which is equal to A into h plus by. Okay, so that this is equal to, so we can rewrite this as W by A, that is equal to RT upon A, so we are taking common terms outside, into 1 upon h minus by minus 1 upon h plus by. Okay, and that can be solved further, that is equal to RT upon A into h plus by minus h plus by divided by h minus y into h plus y. Okay, so after cancellation of the sum of the terms, so this comes out to be equal to T into 2R by upon A into h square minus y square, that is W by A. Okay, or because A and A, they will cancel with each other, so this implies that W is equal to, W equals, I am taking T outsides, T multiply by 2R by upon h square minus y square. Okay, so this is equation number 2. Okay, so now from equation 1, again further we can write from equation 1, I can further rewrite what is the equation 1. So it is Wy, that is equal to 2Cb into T minus T naught. Okay, so from here I can write T minus T naught is equal to Wy upon 2Cb, or from here I can write T, that is equal to T naught plus Wy upon 2Cb. Okay, so let's call this as equation 3. Okay, now equation 2 and 3 implies so I'm going to replace T with this expression in equation 2, so that W comes out to be equal to W, that is equal to T, which is this quantity T, which is T naught plus Wy upon 2Cb. T is equal to this quantity W is equal to T into 2R by divided by H square minus by square. So let's call this as equation 4. Okay, now we are given a condition that W into Y, it is much larger than T naught Cb. So that means Wy upon Cb, this is much larger than T naught. So that means in equation 4 we can neglect T naught as compared to Wy upon 2Cb, because this is going to be much larger. Okay, so therefore W can be approximated as Wy upon 2Cb into 2R by upon H square minus by square. So 2 will cancel with 2, and further here we are going to make use of the fact that, so we are going to make use of the result that Cp minus Cv, that is equal to R for 1 mole of a gas. Okay, so if you divide both sides with Cp by Cb minus 1, that is equal to R upon Cv. So R upon Cv comes out to be equal to, so therefore R upon Cv comes out to be equal to gamma minus 1. So we will make use of this result here in this equation. So we are having R by Cv here, so this is, and W that will cancel with each other. Okay, so that means, so from here this point onward I can write 1, that is equal to R by Cb into by square upon H square minus by square. Okay, so R by Cb, that is equal to gamma minus 1, so that is gamma minus 1 into by square upon H square minus by square. Okay, further upon doing the cross multiplication, we obtain H square minus by square, that is equal to gamma times y square minus by square. So this by square will cancel with by square, and from here we obtain that y is equal to under root h upon gamma. Okay, so therefore the correct option, if we just take a look at the option that are given to us, therefore wait, it is it is h upon under root gamma, because we are having h square is equal to gamma times by square. So y is equal to h upon y is equal to h upon under root gamma. Okay, so therefore correct option is C here.